This program is presented by Community Television. A simulcast can be found on WRFP-LP 101.9 FM.
Welcome to the Chippewa Valley Sustainable Future Festival. Buzz Sorge presents Algae in the Lakes.
Good afternoon. I'm pleased to present Buzz Sorge. He's here to talk to us about our waterways. His expertise includes stream eutrophication research, large river basin assessment and planning, lake management planning, lake limnological assessment, land use planning, lake classification, land use ordinance development assessment, and a lot more. Currently, he's been focusing on lake management planning, nutrient dynamics in large river basins, lake nutrient standard development, and agriculture management practices to reduce nutrient loading. He's going to talk to us a lot more about that, and I'm very happy that he's here for it. Thank you.
Well, good afternoon. So, when I got asked to talk about this, so we talked about what does it take to sustain Wisconsin's lakes, and that's what I wanted to talk about, the threats and what we can do about those threats to lakes. To understand that a little bit, what we have to think about is how do our lakes get to Wisconsin and how many do we have in these lake resources. Well, our lakes really started forming, they're about 13,000 years old. And so we're not making any more lakes, let's hope. And we really have two major lake clusters in Wisconsin. Where you look at the high lake densities, we've got the north central lake cluster and the lake northwest one. And then central Wisconsin has quite a few lakes in it, natural lakes too. And then we also have our lakes, our artificial lakes, our riverine systems. And we really are quite blessed. We have one of the largest concentrations of glacial lakes of any place on the planet. I think Siberia is the only place that has higher densities of lakes than what we have in our lake clusters. And when you think about that, you got to think, and I really want to set the stage, because when we manage lakes, we got to think about doing things on lake time, not people time. We really, our lakes stayed very constant up until probably about 1870s, 1880s was the biggest impact in northwest and northern Wisconsin. That's when the cutover happened. That's when all the white pine left the landscape to build the Midwest, and the landscape was really taken to ground zero. I don't know if people have seen those pictures circa 1920 in northern Wisconsin. It pretty much looked like a moonscape. There was nothing up there except stumps, and then so we tried to farm it for a couple of decades. That didn't work so good. And then that's when our development really started, with some of the lumber barons actually building some of their homes and resorts and summer places on the lake. The oldest one that I know of in this area is the old Basswood Estate up on Long Lake. That was built turn of the century. So when we really think about the development on lake, and that is a key component I'm going to talk a lot about this afternoon, that really started in the early 1900s, but it really kicked in right after World War II when we had those disposable incomes in the society. People had enough money to actually have that second home. So this is kind of what 1940 we use as kind of a base of development. And you think about this, most of that yellow out there of greater than color, greater than 5 to 10 homes per square mile is on lakes. And then if we go to the 1990s, that was the stock market boom and things really went nuts. During the 90s, what happened is all of those smaller lakes that really weren't the high priority lakes, those less desirable lake shores, all of those got developed. And then at that same time, because all that cash was out there in the market, that's when a lot of redevelopment happened. And when we took out the old cottages and put it up the starting castles on lake shores. And this is kind of what we think it's looking out there like now in 2010. We've really got a lot of our lakes maxed out with development. And when we think about these stressors and what do we want to do to sustain lakes, what are we really sustaining? Well, we're sustaining those ecosystem services that lakes provide, the cultural services they provide to our society, and the recreational opportunities out there. And I'll talk a lot more about the ecosystem functions a little later on in the talk, but the cultural thing that I think we think about most when we surveyed probably, I don't know, probably somewhere between 20 and 60,000 people who use and live around lakes. And the number one use all the time that people have around lakes is peace and quiet and natural beauty. It always ranks the highest of all the uses out there. So that is important to Wisconsin people. That's where we go to relax and kind of recruit and regenerate. We like to be near water. And then those recreational uses often come in third, fourth, fifth, fishing, boating, that type of thing. So if anybody's got any questions as I go through the talk, just let's make it interactive and just ask me questions. And so this is what we're trying to sustain, is these ecosystem, cultural, and recreational services that lakes provide to Wisconsin. What are the big threats? Well, the big threats that we have to the lakes in Wisconsin really is excess of nutrients coming into our lakes. I think anybody who heads west, the poster child for excess of nutrients in lakes is Tainer and Monoman. And you drive over the 94 bridge, those lakes have some of the worst water quality, and they're in the worst 5% of lakes in the entire state. And the next thing that we really have had a huge impact, I'll talk a lot more about this, with the way we've brought those urban value systems to those lake shores, we've really destroyed critical habitats of our shoreline habitat, and this is absolutely important if we're going to sustain these ecosystems. And then aquatic invasive plants and animals are the more recent threats. And so these are the things I'll spend the next half hour or so talking to folks about. So in order to understand how these issues are impacting lakes, all lakes don't behave the same. So we got to talk a little bit about the different types of lakes that we have in Wisconsin. And we categorize them as seepage lakes, groundwater drainage lakes, impoundments, and then oxbow lakes. And a seepage lake is simply a lake that was formed by a block of ice that was broke off the bottom of the glacier, pushed down into the Earth's surface and created a depression, and then simply it gets filled by groundwater. Groundwater is moving underneath the landscape, very similar to the patterns that our surface waters flow. And so on a seepage lake, it's dominated by groundwater. It's water in one side, water out the other side. And the thing about seepage lakes is groundwater moves extremely slowly. And so the water in these lakes stays in there a long time. And I'll talk a little bit more about that later, why that's important. This is just a whiteout of a piece of Chippewa County landscape. This is Round Lake up near the Rusk Chippewa County border up by New Auburn. And that's kind of the way that seepage lake landscape looks. I mean, there was just all these ice blocks that were just broken off the bottom of the glacier, created these depressions, and all those depressions have filled with water. And we've got quite a few of these seepage lakes up in Chippewa County. Groundwater drainage lakes, it's got a little bit bigger catchment area. It's still dominated by groundwater. And what we say, these types of lakes, they sit up near the top of the landscape. They're high up in the landscape because they don't have much land that runs to them. But they do capture enough water where they create an outflow. These are the headwater lakes of streams. Sand Lake is a very good example of a groundwater drainage lake. Here's the Chippewa County line about here up on Highway 48. And so that's a classic example of a groundwater drainage lake. Long Lake, drainage lake. Now we're into lakes that have a little less groundwater influence, a lot more surface water influence. They've got bigger catchments. They're a little lower in the landscape position. Water flows through them a little bit quicker. Long Lake is a drainage lake. We have a stream coming in about here and then one out there, and then it goes out into the island McCann chain. Impoundments aren't really lakes at all. They're just dammed up pieces of river, and they're man-made lakes. These are kind of the problem children for lake managers. Tainer Lake, Monoman Lakes, they're all dammed up pieces of river, and they have very large catchments, and very large amounts of land draining to them. Lake Altoona, I use that as an example often. Lake Altoona has a real unique problem. It's very low in the Chippewa River system. Lake Altoona receives 111,000 cubic yards of sediment annually from the Eau Claire River. Do divide that by 15, and that's how many dump truck loads of sand they have to deal with out there on a routine basis. When we started the first dredging project, probably over a decade or more ago, the lake was really filled in to about down there when they started that first dredging effort out on Lake Altoona. Consequently, Tainer and Monoman Lake are also very low in the Red Cedar watershed. They receive about 600,000 pounds of phosphorus annually from the land that drains to Tainer Lake, and I'll show you why that's problematic.
How many pounds did you say?
It's about 500,000 or 600,000 pounds a year. In 1990, and it was about a week in March, the spring runoff had been over 300,000 pounds of phosphorus came through Tainer Lake.
How would that compare to Lake Altoona phosphorus?
Phosphorus, they have the Red Cedar system's much higher in phosphorus. We'll see concentrations in Lake Altoona. I'm thinking that's probably often in that about 60 to 70 microgram per liter range. Often in Tainer and Monoman we'll see about double that. And lakes start experience nuisance algal blooms when you get above about 20 micrograms per liter. Lake depth matters. Deep lakes behave much differently than shallow lakes. For the same surface area, if you have a deeper lake, it's kind of dilution is the solution to pollution. You've got a lot more water in a deep lake simply. You put the same pollutant load into a deep lake, you aren't going to get the same response when you put that into a shallow lake that may only have about 25% as much water as a deep lake. And so our shallow lakes, they often tend to be a lot greener than our deeper lakes because of that, unless you have a lot of aquatic plants in them. So sometimes a shallow lake will sustain higher nutrient loads to it if it's full of aquatic plants. If you've got a shallow lake that is very dense with aquatic vegetation in it, it might tolerate a phosphorus concentration up into the 70, 80 microgram per liter range and stay perfectly clear. But if those plants aren't in there and there's that much phosphorus into them, then they get very, very green and full of algae. What drives all this on the landscape is the hydrologic cycle, and we have to just take a minute and talk about that a little bit, because in this part of Wisconsin we get about 30 plus inches of rain a year on average. Of that 30 plus inches of rain, only about 7 or 8 of it actually make it into the Chippewa River or into a lake. A lot of it goes right back up as evaporation or transpiration by the vegetation. Some of it goes to deep groundwater, and then a very limited amount of it, about a quarter of it, is all that makes it to stream flow. And this is what I was talking about, why it's important how lakes are different, the amount of land that drains to a lake. This is that round lake I showed you up earlier in the landscape, and it's land that drains to it. Round Lake only has about 2 acres of land for every acre of water that drain to it. And consequently, it's got a very low phosphorus concentration, and it just doesn't have much land feeding to it. As opposed to Tainer Lake, I think it's around 1,100 acres of land drained to every acre of Tainer Lake. So we have huge land mass in these, in our large riverine systems.
Why is that? Because of the watershed's slope or soil?
Just at the bottom of a river. It's a dammed up piece of river. And this is a natural seepage lake. Again, this was created by that ice block, and it was sitting up in that glacial landscape, and there just isn't much downhill before you get to the lake. And in Tainer Lake's case, downhill starts clear up in Big Shatak Lake north of Birchwood, and everything from Big Shatak all the way down through the whole Red Cedar system ends up in Tainer Lake and all the land and small tributary streams along the way. Chemical characteristics, are really important. I'm going to really just talk about the nutrient phosphorus a bit. The nutrient in least supply relative to plant needs, it's understood since about 1849, controls the growth of plants. Out on the Wisconsin landscape, in our natural landscape, naturally we had very, very low levels of phosphorus here. We would have sampled soils prior to about 1930 in Wisconsin. Our soil tests were probably about 15 to 20 parts per million. That's changed dramatically. There just wasn't much out there. So anytime we can have that phenomenon occurring, we can manage that nutrient at least that supply to control the growth of plants. And in lakes case, in all of our lakes in Wisconsin, greater than 90% of them, they're what we call phosphorus limited. And what that simply means, every additional unit of phosphorus we add to a lake, we can grow more algae. Conversely, every unit of phosphorus we can take out of these lakes, we can decrease the lake's ability to grow phosphorus. This was hardly debated in lakes back in the 70s and 80s, back when I was in grad school and was just kind of getting sorted out. And in those days, what we were fighting over, it was the Clean Water Act that just passed in the early 70s, and we were thinking about how we're going to clean up all these riverways across the country. And one industry that kind of was balking at doing their part was the soap and detergent industry. So they were funding all these researchers to determine what is the limiting nutrient in lakes. And so they had a bunch of folks that carbon's an essential nutrient for growth, so they had a bunch of guys that were trying to make case it's carbon limiting algal growth in lakes. Then they had another batch of folks that were thinking it was nitrogen, and they really weren't gaining much ground. And independently, a researcher up in Alberta named Dave Schindler, he had this pretty much all figured out. He was doing his PhD, and everybody pretty much was thinking it was phosphorus. But what Dave simply did was he put a rubber curtain across this lake, and he fertilized both sides with all the carbon and nitrogen that you needed for plant growth. And then at one side he just added a very limited amount of phosphorus, and that was the algal response Dave got out of that lake. And that was the definitive piece of science that just says, folks, let's focus on this element phosphorus in these glacial lakes that we have in southern Canada and the upper Midwest and the Finger Lakes area, New York and Maine. So ever since then, what we really strive for is pulling phosphorus out of most of our lakes. We have a handful of lakes in this state that are nitrogen limited, and there isn't really much you can do about that, but it's really this element phosphorus. And in Tainer and Monoman, what we're really working out on, for really all the lakes that I work on in this whole part of the state, is how do we minimize that phosphorus delivery system to those lakes. And that is the big threat that threatens their sustainability. It's really surpassed it in a lake like Tainer's case. I mean, we'll talk more about that because we've got some very significant issues here. And so this is just basically, we index the amount of algae in lakes with the greenness in there. We filter the algae cells out of the water, crush those cells up, and we just measure the mass of chlorophyll in them. Then we can also measure the mass of chlorophyll in our phosphorus samples. And this is data from hundreds of lakes. And you can see we get this fairly definitive relationship. You put higher the phosphorus concentration, the higher the algae concentration, and you can run that line backwards. The lower the phosphorus concentration, the lower the algae concentration. Where thresholds for lakes really are, most people will really swim in about 20 micrograms per liter algae chlorophyll. And that's just a slight green tinge. If you're out there on the water, you can tell there's algae in there, but the water still looks pretty good. Once you get much above 20, especially if you get up around 50 micrograms per liter chlorophyll, which is 20, 30, 40, 50, you're out here up in the 70, 80 microgram per liter range. Phosphorus, that's when we start to have human health issues. That's when we have blue-green algae cells that exceed 100,000 cells per milliliter. And once we hit that threshold number, that's when we can have the presence of blue-green algal toxins present. So that's pretty important. These ecological services I talked about a little bit earlier, really it's sustaining this whole lake ecosystem. You got to have the algae at the bottom of the food chain. They have to be high enough quality algae so the zooplankton can eat them, and then so the fish can eat the zooplankton. The algae really, what they are, the primary energy source out there, and as long as we can maintain an algae population in a lake that's dominated by a green algae, we're in pretty darn good shape. Because the cells are small, they're very productive, but what the next level up in the food chain can eat those cells in. But if we get into the blue-green algae, that's when we get into our nuisance levels. That's more these longer filaments, these bigger cellular structures. That's when we begin to have the human health problems, the nuisance, the odor, all those issues begin to show up in lake ecosystems. Aquatic plants, these guys are absolutely critical to lake ecosystems. Most people don't like them by their peers, but they're absolutely the fish factory out there. It's where the fish and a lot of invertebrates they are habitat for that. They provide a great buffer against wave action in that near shore zone, so they help protect against shoreline erosion. And again, they're oxygen producers, which is needed to sustain the life in any lake too, as well as the algae are. These are my favorite guys in lakes. Giant one of these guys is about 1.5 millimeters inside. One of those, that's a Daphnia. It's a zooplankton. What these guys are able to do, little guy like that can put about 1.5 liters of water through himself in a day, filtering all the algae out of the lake. And so what he has to be able to do, he actually is bivalve, so think of him almost built like a clam with his legs here in the middle. He's just bringing that water right through, and what he's doing is ingesting those small green algae cells. And this is your meat and potatoes, your steak for your young of the year fish. You've got to have a healthy zooplankton population if you're going to have a healthy fishery, because that's the first thing larval fish go out and look for to feed upon, is zooplankton. Then we get into some of our bigger invertebrates, which are also great energy sources for our fisheries, and they're also fun to watch. Dragonflies hunt packs because they nail a lot of mosquitoes around lakes, and if you don't ever watch them, pay attention to a pack of dragonflies. Sometimes they hunt as a unit. They've got a strategy. Fish, what we really see is a wide diversity in our fisheries out there. What we really want to see is kind of a what we have mostly around here is panfish, largemouth bass lakes, and with climate change that is occurring, this is a thing that's a phenomenon that's going on across the north. Our fishermen hate it because they're losing their walleye fisheries. Anybody that pays attention much to fish, everybody's saying, well, there's a lot more largemouth bass in our lakes. Well, part of that is because people don't want to eat them. We've gotten people to be really good at catch and release. So a lot of these big guys, they just get dumped right back into the lake, and they are a top predator, and they eat a lot of small fish. So what we're seeing though is a lot of our fisheries converting from walleye lakes to more dominated by smallmouth and largemouth. And it's kind of a double function because lakes are getting a bit warmer with climate change, which favors bass over walleyes. Walleyes are a cool water species, and so this is something to kind of watch. You'll hear quite a lot about it, and it's one of the things people really want lakes to stay walleye lakes. Well, ecologically, they probably won't, just because of climate change. When a lake really gets out of whack, we can get them dominated by carp or bullheads. Half Moon Lake, if folks who have lived in Eau Claire for the last 40 years, probably if you remember the late 70s, long before I got to town, Half Moon Lake was full of carp. And they did a rotenone treatment on Half Moon Lake in the 80s sometime and restructured that whole fishery. And we have to do that sometimes. I just participated in a project like that down in Lake Toma in the fall of 2010. We kind of reset the clock then. So you can manage that on certain systems, where you come in with chemical called rotenone. It's a natural organic fish toxicant. And what rotenone has been used for centuries by Aboriginal cultures in South America to fish with. It comes from a plant, it's a Daris root plant, and they simply have been capturing that root for many years, and all it does is you put it in the water and it just clogs the oxygen transfer across the gill membranes and the fish suffocate. And it's been a great, they've been fishing with it for centuries. So some people get, it's a much safer fish toxicant than what we used to use back when I was in undergraduate school. At that time there was a fish toxicant out there, it was anamycin, and it wiped out everything in the aquatic ecosystem, so we don't use that anymore. But we don't do many of these restructuring projects anymore, maybe one or two in a decade across the state. How do we measure when lake water quality starts to go bad, and what are some of the signals we look for in lakes? The easiest one is simply measuring water clarity. We have several hundred people across the state of Wisconsin that measure water clarity in their lakes as volunteer monitors. And what we can then begin to do is track over a longer period of time the health of that lake by just simply measuring water clarity. This is a simple black and white 8-inch disc called the Secchi disc. It's the most common limnological tool out there we have in the toolbox. And we get tens of thousands of these readings across the state every summer from a lot of great volunteers. Another tool that we have in our toolbox is called paleolimnology, and this is a really important tool because what this tool allows us to do is reconstruct the water quality history of all of our natural lakes in the state. And if you think about how do we do such a thing, well, a lake gets a layer of sediment every year, a fresh layer of sediment, just like a growth ring on a tree lays down another ring. Well, we can take a core down through those sediments, and then within each layer of sediment in the lake store the water quality history of the lake. And it's stored in there with special kinds of algae called diatoms. Diatoms, they're cellular structures made out of silica, and they're very unique. Each species has a very, very unique cellular structure, and we can tell the good guys from the bad guys, and then we can equate that to the phosphorus concentration that was present in the lake at the time that sediment was laid down, and then we can reconstruct the water quality history of the lake. One of my favorite ones, one of the first ones I was involved, was Squaw Lake out in St. Croix County, up northwest of New Richmond. Boy, when I got up here in the mid-'80s, everybody thought Squaw Lake was just horrible water quality and had been that for centuries. Well, not so. And when a friend of mine, Paul Garrison, one of our research limnologists, Paulie came up, we popped a core on the lake, and when we started looking at it, it exhibited the classic symptoms. We see the same structure, but maybe not to the same degree. Water quality. The green is the chlorophyll that's stored in those sediments, and both of these, I can't remember, the red's the amount of organic matter, but they both mimic phosphorus at the same time. And what we saw in Squaw Lake was things stayed pretty good until the early 1900s when we started farming that watershed out there. This has about a 2 square mile egg watershed to it, and the lake's ringed with development. That's pretty important. The other thing that we've learned about Squaw Lake only gets runoff during spring meltwater. The soils are such out there, you can dump all the water on that watershed, unless that ground's frozen, none of it makes it to the lake. So what we see at about 1940 is what happened, and if we think about 1940, what did we get besides bombs from World War II? We got fertilizer. We got ammonia, nitrogen fertilizer for corn. That was one of the processes that those Germans figured out in their bomb-making exercise, and we also figured out how to start mining phosphorus to put it on the landscape to go away commodities. So virtually, you think those soils probably were opened up around 1860, late 1800s. That's when we see the farming in the watershed. You start to see water quality decline. But it really starts declining more when we put phosphorus on it, but we really see this precipitous decline in water quality in Squaw Lake about 1980. Well, about that time, there was a farmer out there, his name was Russ Strobing. Well, what Russ wanted to do, it's pretty cold in the winter, so he just hauled his manure across the road from his barn, and he piled it, happened to be in the floodway. Well, then about that time, we had a lot of snow then, a lot of meltwater, the manure pile became inundated for a couple of winters on the spring melts, and all of a sudden we really had bad water quality in Squaw Lake. Then Squaw Lake has another nasty little characteristic. It has the ability to self-fertilize itself from all that phosphorus that's gone into the sediments over the year. The great news about the Squaw Lake story is in a couple of weeks they're going to be giving their lake management plan to their lake district, and they can take water quality right back to here with some of the work that they've done out there in the watershed. Their farmers have been excellent. They've all stepped up to the plate. We actually have more phosphorus leaving that watershed now as meat, milk, and corn and beans than we do coming in to produce it. That's called a negative phosphorus balance. The only watershed I know in the state that's in that case. And the farmers are talking about infiltrating all that spring meltwater out in their fields. We're just going to store it. When the frost goes out, it'll go down. And then we'll seal up their bottom sediments, much like it'll be a very similar project that was done on Half Moon Lake. And we hope to be able to restore this lake to almost a pre-settlement condition. It'd be phenomenal.
You said this Squaw Lake though could self
fertilize itself.
Yeah.
That's the same thing Half Moon Lake was doing. That's why we controlled the plant population down there, and that's why the ski sprites had to leave down there. And then that's in 2011. That's why we dumped about $350,000 worth of aluminum sulfate on the bottom sediments. What aluminum does with phosphorus is it makes an insoluble complex. Once an aluminum ion grabs a phosphate ion, it's there for perpetuity. What's naturally going on in lakes, on the bottom of lakes, if you think about it, it's iron is functioning in that role. And that only does that in the presence of oxygen. As soon as you go anoxic, like most of our lake bottoms do, the iron goes to from a +3 state to a +2, and the phosphate ion gets to float out, and it's algal available and stimulates algal blooms. And that's the phenomenon we have to seal up to take care of the sins of the past, that phosphorus that's there in the bottom sediment. So, harmful algal blooms. This is my favorite lake, Tainer Lake. I wish it was a little clearer. This is a very typical condition for either Monoman and Tainer anytime from June 15th to October 15th. It was just extremely, you can see extremely high amounts of algae. Remember I said that around 20 micrograms per liter chlorophyll, you're not going to want to swim in it anymore. We routinely see concentrations in Tainer Lake during the summer from 100 to 200. It's just the way the lake is. And blue-green algae are the problem with this. And blue-green algae have, they're gram-negative bacteria is what they really are. And that's the same thing E. coli are, the same thing salmonella are. And so you can get some reactions from blue-green algae by just walking in the water, even in the absence of the toxins. There's an organic chemical in the cellular structure of the cell wall that is an irritant, and some people will react to that. I think I've got the famous foot in here. No, this is also what it kind of looks like on any given day, some days. But so those blue-green algae do have the ability to produce toxins. I'll talk a little bit more about that. We've surveyed, I don't know, I think there's 48 lakes in this data set where we've documented blue-green algal toxicity in these lakes across the state. If you take just the largest 8 lakes in the state that exceeds 200,000 acres of water that we have documented the presence of blue-green algal toxicity. Lake Winnebago obviously makes up a lot of that, but if you take Petenwell, Castle Rock, the Big Old Plain, Monoman and Tainer, Lake Wisconsin, and Beaver Dam Lake, think of the economic impact of not being able to use 200,000 acres of water in the state of Wisconsin for body contact recreation. It's a huge impact.
Are most of those impounded lakes, or doesn't it matter?
Wisconsin, Pete Mullet, Castle Rock, Big Oak Plain, they're all impounded lakes. Tanner and Menominee. This cluster out here in Polk County, I don't think are. Winnebago's obviously a natural lake, and Beaver Dam Lake is a raised lake. It was a big shallow marsh and they put a dam on it and raised it. So, am I about done?
No.
Okay. This is the foot. This is one of our employees. It was Deb Conkle. That's that reaction, that rash reaction. Deb was loading a boat one night out on Tanner after did a plant study out there that day, and she got back, processed our plants, and she had that sock in contact with her foot for 3-4 hours. That's what she woke up with the next morning. Another researcher, he did it, comes out of down at the Center for Limnology in Madison, Peter Johnson, started looking at some of these very blue-green algal-dominated small lakes, and that's where Peter began to see a lot of frog deformities in some of those systems, and he was able to do the research to determine that that can be one cause of the frog deformities we have seen is in these high-density blue-green algal-dominated lakes.
Does that affect the fish and our consumption of fish?
We've never had a fish issue associated with anybody consuming fish out of any of these lakes. So when we think about blue-green algal toxicity, they can really develop, it's really three major genera. It's Anabina, Microcystis, and Amphanozomnon are the three types of blue-green algae that do this. But it can be a hepatotoxin, which is if you ingest it, it can cause liver impacts. There's a friend of mine over on Tanner Lake, his son can no longer come to visit them in the summer because he's got a chronic liver condition and his doctor says don't go over there. It can be a neurotoxin. That's what we think about. 8 or 9 years ago, a young man at a bachelor party went for a swim one night down in Madison. He died and they determined it was a neurotoxin. He had an acute reaction. We have several dog deaths over the last 10 years. You might get one every 2 years, a couple a year. Pets drink this stuff and they'll take it on, and that's usually the hepatotoxin, the dog deaths. And then the dermal reaction, like Deb's foot, where you can react with the skin reaction. So what's causing this stuff? Well, how have we modified the landscape that eutrophies or adds all these nutrients to the lake? Well, we've really done two things. As we develop a lake, we make the landscape very efficient at transporting water. We want to get that water away from our buildings. And with this type of development, what we really do, we increase the amount and rate of runoff coming off there by about an order of magnitude over a natural state. So you get about 10 times more phosphorus coming to a lake because just how we've developed them. So we have to really think about how we can deal with that is stormwater management. I think Dan Zur gave a talk earlier today, and so I'm not going to get into that too much. And we've done the same thing out there on the agricultural landscape. Remember I said when pre-settlement condition we had about the phosphorus concentrations in our soils about 15 parts per million. Average soil test P now in the state of Wisconsin is 50. So we've increased it by about a factor of 3. If you get close to any dairy barn, and I've sampled my own pastures around ours, that number can go up to 200-300 parts per million phosphorus in there. And so you start running that water over those high phosphate soils, we see a lot of phosphorus in agricultural runoff. And again, we've made the fields very efficient at getting rid of water so we can produce those agricultural commodities.
There are fertilizers without phosphates now.
Yeah, and a lot of farmers are doing.
Why are we still having such?
Well, it's residual since it's past. I mean, it's that bank we put out there on the landscape. Yeah, I mean, these large dairies today that we're dealing with, our CAFOs that we're permitting, they're actually putting very little phosphorus on. They don't hardly do any, and that's by design and by permit often. So when we think about this, it's just that transport process. I'm running a little short here, so it's very similar to the hydrologic cycle though. Put that rainfall on the ground out there. that stuff that comes off as surface runoff. Some of that is going to move actual soil particles. Some of that phosphorus is going to desorb from those particles right into the water. What we see on agricultural land runoff, maybe 50 to 70% of that runoff, the phosphorus in it is algal available. And depending if it's a manure application or just coming off of a field that hasn't had manure, we'll generally see about 1 to 4 milligrams per liter phosphorus in that runoff. Our sewage treatment plants in Wisconsin today, an average sewage treatment plant only delivers at about 0.7 milligrams per liter in the runoff. So runoff off agricultural land may be 2 to 5 times worse. That's what's coming out of the end of a pipe in a sewage treatment plant today. And the other thing, how come we get that order of magnitude increase in that runoff as we develop a property? Think about this. What we do is we really turn that soil around a house when we build it into just like concrete. You're on there with track hoes, dump trucks, cats, all this heavy equipment, and that soil loses all of its soil structure, and then it no longer can infiltrate water. And if you just put a normal yard in like this without some of the techniques we have today and let earthworms do their thing on that soil, it'd take that yard about 50 years to get its infiltration capacity back. But there are ways to speed that up now, and many techniques are out there. Both Wisconsin and Minnesota now have for lawn fertilizers are 0P, and even this lawn here will load at about 7 times background. So, ag impacts, I think I've talked quite a bit about that. You know, we're doing a lot better, and we surely have all the technical understanding to solve these problems. That is a non-issue anymore today. What we simply lack is the political and social will to have the behavioral changes we need out there in the agricultural landscape to manage this runoff in such a way that it doesn't cause a water quality impact. Here's just a little tidbit. Remember I talked about how we put all that phosphorus out there on the land through animal waste and fertilizer. A friend of mine, Elena Bennett, when she did her master's research, she really did for Lake Mendota what we did for Squaw Lakes, where we learned how to do it. It was from the work Elena had did. What this equates to with what we were taking to grow all the egg commodities and produce the milk and meat and corn and beans in the Lake Mendota watershed. The net increase in Lake Mendota for years was we were putting on 1 million more pounds of phosphorus than we needed to produce those commodities. So we were really using that watershed as a phosphorus dump site. And it's just the one they chose. It's no different than any other one across Wisconsin. This is how we were farming in the 70s and 80s and 90s. Thank gosh, with nutrient management strategies, those behaviors are changing. Metric tons, 1,000 kilograms, 575 metric tons. So, I always talk about habitat. God, I always talk too much. And I've talked a little bit about that. This is what we would love our natural lake shores to look like. But with those values we have, all of this Western European heritage, we got to have things neat and tidy. And so this is that value system we've often brought to our lake shores. This is absolutely this critical zone right here from about 0 depth out to where light can hit the bottom. That's called the littoral zone, and it's simply that depth that where light penetrates far enough to grow plants on the bottom. In this zone of any lake, 95% of the species in that lake are dependent on that zone for some portion of their life cycle. And these are the kind of guys that are living there that we don't often think about, but these are the kinds of things that we value most. And without those nearshore habitats, these are the ecosystem services besides the fishery ones, and I'll get into that a little bit more. All these are gone with that pattern of development that we have used on Wisconsin lakes. And we've indexed and measured this. We've probably got 15 pieces of science that we've collected since the mid-90s to present, and go through those a bit. In Wisconsin, with our current shoreline zoning regulations, you can build out to 52 homes per mile, 100-foot lots. Where we see all these ecosystem services being lost from all these different pieces of science, we've looked at birds, herbs, bugs, fish, plants, I'm trying to think what else, wood. You get to about 32 homes per mile, those systems are gone. Those ecosystem services are gone from those lakes. The one that I can't believe doesn't gain more traction is this was I'm trying to think of this guy's name. This Center for Limnology study back in I'll get it here shortly, and they saw the same thing. What this researcher simply looked at was in a natural lake ecosystem. Think about it. You got all these trees flowing down over the years, right? They just fall into the lake. From some research out of Ontario, what we learned is, you'd think, how long does a tree provide habitat if it falls in a lake? Well, so somebody went back and started looking, and I think what Bill's last name was, but it was in some Ontario lakes, and what he started looking is, and he's trying to figure this out, he did use the forestry technique where you cut the ends of logs off, then you can actually tell by the growth rings and the weather patterns how old that tree was and when it fell in. Well, what he found out, he had trees that had fallen in the lake 700 years before that were still providing habitat in the Ontario lakes. He also did some hardwoods. They were lasting a mere 400 or 500 years. So what we tend to do when we develop those lake shores, again, to make them leak, we pull that wood out of those systems. And again, you get into this 28 to 30 homes per mile, all that woody habitat is gone from northern Wisconsin lake ecosystems. The big thing we learned out there, and this was actually Dave Schindler's kid, did his PhD down in Madison, and what he found out when he started looking at the growth rates of bass and bluegills, without that wood in those lakes, we've taken 66% of our fisheries production out of our northern Wisconsin lake ecosystems. What's the economic value of that? Conversely, if we thought we had that wood put back in there, we could increase the fisheries production by a factor of 3 if that one habitat component was back in those lake ecosystems. This is what we'd love to see those natural lake shorelines look like, and we do have a big hunk of this. We're doing some of this work up on Long Lake in Chippewa County, where we've probably eased, well, I think we got 11 miles of shoreline on Long Lake, and I think we have close to about 4 of it under conservation easement with conditioned development, where it will look like this in perpetuity, and the homes are all built. These are some very valuable homes up there, and they have zero discharge to the lake. You can do this stuff, and you can have a great lake home at the same time. Aquatic invasive species, this is that third thread I wanted to talk to you about. If we kind of look back through history, this was probably the first guy that showed up was curly leaf pondweed. This was the plant that we were dealing with in Half Moon Lake that was extremely problematic. Anybody, if you remember the summer of 2007 on Half Moon Lake, you could have walked across the lake. There was so much of this plant in the lake. We had 150 acres of it. What this plant does and makes it so successful is it starts growing in about a month from now from this year's fruiting bodies. And it'll throw on about 6 weeks of growth in the fall. It'll get about this height. And it'll sit like that under the ice. As soon as the ice comes out and the lights turn on, this plant starts to grow. It's growing when the water's about, just above freezing. And it does quite well. It's a northern European species. Eurasian water milfoil is the one that you've probably heard a lot about. We had some of that showed up in Half Moon Lake. That has been, we have about, I think, about 450, 500 lakes where it has Eurasian water milfoil in it in Wisconsin now. It only becomes problematic in about 10% of the lakes it gets into. So most of the lakes it gets into, it actually just becomes another plant in the plant community. These guys are showing up. They've been around for the last 20, 25 years. Zebra mussels, they're very problematic over on the Mississippi River and on the Great Lakes. This little guy, rusty crayfish, it's up in Meg's Leg. It's up in Long Lake. And I did my first plant study in a lake right out of undergrad. It was on Long Lake. And we probably had several thousand of these per square meter on the bottom of Long Lake. There were no plants in Long Lake. The crayfish ate all the plants. I mean, you snorkel down there, the bottom would just move with crayfish in the shallow water zone. Today, through some great fisheries management regs up there, where they have one smallmouth bass over 20 and only 10 panfish, these things are highly susceptible to predation when they're about that big and they're molting, and those smallies and the big gills have knocked them out. We now have about 130 acres of plants back in, which is key habitat in Long Lake. A lot of the locals don't like it. They aren't used to having plants in their lake, but we've got great diversity of aquatic plants. That management strategy worked. The management strategy to knock these two out of Half Moon Lake has been highly successful. This plant was eliminated in one chemical treatment back in, I think this is year 4, must have been, we started in 09, and we had it in there 1 year, did a low dose 2,4-D treatment. I'm not a proponent of using herbicides. We tried many other strategies, we couldn't get it out. But we did use herbicides and did a whole lake low-dose treatment. It was highly effective. And from 100% of the lake surface being covered by this stuff now, it's less than 1%. So it is working. Native species have come back into Half Moon. These guys are the Asian carp. There's 5 or 6 species of them. The story's out on them. Their genetics, their DNA has showed up in the St. Croix. It showed up as high as Minneapolis, St. Paul. They're in the Mississippi River system. Those are something we don't want to deal with. They disrupt all the phytoplankton. They disrupt the zooplankton, all the natural feeding processes of all of our native fishes. They could become extremely problematic. And who knows what's the next invasive species is. How do they get here? This is how they got here. I saw a great slide a couple of years ago at a meeting, and it showed the amount of ship traffic around the globe, and it just started lightening up the globe with lines. I mean, the world is an extremely small place. Into our ports on the Great Lakes, up the Mississippi, we're connected to the rest of the world. These guys take on ballast water, so they don't tip over when they're not loaded. That ballast water may have come from China. That ballast water may have come from over by Europe someplace. That's how these things originally get here. And after they get here, this is the next way we get them around. Boat trailers. You think about a new boat today, I don't know how many feet of plastic tubing they have in them between their live well and bilge pumps and everything. Most of these species, plants can just catch a ride on any trailer. We have very good plant laws now in Wisconsin. We also have a very good strategy of citizen volunteers manning boat landings. So why do we care? It sure is an economic impact. Lakes that are full of Eurasian water milfoil or some of these carp species or whatever, people don't want to recreate there so much if they use one of those uses or values they have for the lake. It's very expensive to control them. Ecological impacts can be huge on any given lake, as well as the boating impacts or recreational impacts. So what's our program to sustain lakes in Wisconsin? What we really have is a great network of several thousand volunteers across the state. It's called Clean Boats, Clean Waters. People who live around lakes and care about lakes man boat landings and just talk to a lot of folks to make sure they understand this is not acceptable behavior in Wisconsin. One, you can get a ticket for that now, that's fairly significant. And two, that's curly leaf pondweed, and you don't want to be the transfer mechanism. And the other, we call that prevention, where lakes that don't have an invasive in them yet. And then we have a containment process too, where lakes already, there are systems that do have invasive species. And so we want to make sure when people take their boat out of those lakes, they understand, go wash that thing down with hot water someplace, or at least don't put it in another lake for 7 to 10 days. So it's prevention and containment. Talked about that. And these are all the various program elements we have. We spend a lot of time on education and outreach at Clean Boats, Clean Water program. We have a part of our citizen lake monitoring effort. We have trained folks how to monitor the lakes for the presence of invasive species. We have people, purple loosestrife was a big threat to many of our wetlands in Wisconsin. Oh, back in the mid-'80s, I came up here out of southeast Wisconsin. Most of those wetlands down there in southeast Wisconsin, they were this beautiful magenta this time of the year. Today, you can hardly see, you don't see very much of this, and that's all been with a volunteer effort of the successful biocontrol of a Galeanis beetle. A lot of folks started raising those beetles and started releasing them on populations of purple loosestrife. We restored and sustained those wetland functions back to their native species. The biggest one that folks might be able to relate to was when you're going up Highway 27 just after you cross the Jump River Bridge on Holcomb. If you remember, off to the left up there, that used to be all purple. Brian Goodman, the egg teacher, took this on up there. He became the purple loosestrife czar of northwest Wisconsin. His kids started raising these beetles. They eliminated it in about 8 years from the Holcomb system, and then he was teaching other folks all across the north how to do that. Spend a lot of bucks on research, and then we've got a lot better rule and law package to help prevent the spread. So that's it. Sorry I went over a bit, but...
Well, you started late, so.
Oh, that's right.
Thank you.
Any questions?
Yes, I have another one.
Yeah.
Lake Altoona, that's okay.
Yeah.
Why are there no weeds?
A couple of...
Sediment and...
One, it's got a sediment type that's not real conducive to a lot of aquatic plants. Sand doesn't grow plants very well.
Not a very good diagnosis.
Yeah, we're seeing better
Healthy
plants.
lake, right?
Well, no. Well, another thing, a management strategy that we've employed out there is elimination of the winter drawdown. When you expose that lake bed year after year, not many plants can sustain that type of exposure. So with elimination of the drawdown, what we're hoping to see is somewhat of a bounce back of the aquatic plant community out there on the lake. And where we hope to find plants is where we should find plants. You need a good mix of some organic ooze and sand. That organic matter has a lot of nutrients in it, and that will sustain those. The Eau Claire River system is a dark water system by nature, so you don't get a lot of light penetration in naturally dark water systems. That will limit the plant growth. Like the plant rooting depth, like up in, let's say, Sand Lake, up in Clearwater system, we'll find plants growing down to about 22 feet. We get enough light down there. You go into our Eau Claire system, you probably won't see a good day if we didn't have much for algae blooms that summer, 7 or 8 feet max. And that's just natural light limitation.
Is Lake Monoman and Tainter salvageable?
Oh, absolutely.
Okay.
There is no reason we can't, one, eliminate the human health concerns we have over there, and then reduce the frequency of nuisance blooms to a point where you may, right now we would have 0 days that I would say would meet the criteria for suitable body contact recreation by our models. We should be able to at least have 50 to 60 days per summer, with, if we can, minimize the agricultural runoff that comes out of that watershed. Again, it's a behavior change. It's not a technical fix. We understand the technical stuff we have to do. It's getting farmers to implement those practices onto the landscape. Yeah.
What have been the most successful strategies for getting farmers on board? At least how did St. Croix farmers become such a advocate from a time?
Well, we're actually going to try a new strategy that we're going to pilot here in western Wisconsin in the St. Croix water basin and in the Red Cedar. And this comes out of some pilot work that was a combination of some stuff that's been done over in Minnesota and Iowa State, down out of the Leopold Center in northeast Iowa, and some stuff out of Dane County, Wisconsin. And what we've done is taken the best of those three strategies and we're putting that into one watershed management project that we'll be moving online here probably in October. We're in the process of getting the people hired. Hopefully we'll get our McKnight grant next week and our DNR monies. And it's a farmer-led model where these folks out in Iowa work in neighborhood groups, small watersheds that 20 to 60 farmers in a group. And it's really a farmer leadership development program. And these farmers then come together as in these farmer councils, and they start making the decisions on, once they accept their responsibility to reduce the runoff, they're in charge. And they figure out the puzzle with technical assistance from, we're going to use our land conservation department staff in Dunn, Pierce, Polk, and St. Croix counties to help the one-on-one with farmers, but the farmers are really going to lead their councils, and they will decide the strategies, and we're taking away the cost share incentives. They're not going to get the check in the mailbox on a so much per acre. We're going to give them a lump sum, a modest amount. In Iowa, they found that anywhere from $700 to $1,500 was enough per year to get farmers to do this. Think of this. If you were to do nutrient management planning in Wisconsin right now, you would get a cost share to $28 an acre. If you farm 1,000 acres, you get 28 grand to do that. That's real money. We're only going to put on the table about $1,000 per farmer, no matter how big you are. And they will measure these things. What we've also learned from our Dane County work is the landscape's not equal and how it delivers phosphorus on agricultural lands. We see anywhere from 20 to 40% of the land delivers 60 to 80% of the pollutant input. So we call them we call them the red fields, because that's how they got mapped down in Dane County. No farmer likes to have a red field on his farm. The red fields just went away without any cost sharing. There's a lot of peer pressure that goes on out there in the rural landscape, so you light these fields up. And then what we've also learned out of our friends in Minnesota is a concept that's nothing really that new. It's civic engagement. It's how do we get people like ourselves actively involved in good public policy decision making. And we're bringing that strategy into this project also with these farmer councils. Yeah.
What would you say would be the cause of a high phosphorus content, excessive weed growth? I live on a small lake that has no agricultural runoff.
We're at
Taylor County.
You have a unique problem in Taylor County.
Yeah.
What we've got, there's a lens of soil. We happen to be right in line with North Dakota. And there's a loess deposition area. And loess is a soil type that's wind blown. It's kind of was glacial flour. There were some really high levels of phosphorus in some rock out in North Dakota that got ground up really good. And there's a lens of that got blown across. It starts over in Polk County, comes through Russ, and right over to Taylor. And it's a natural high level of phosphorus in the land out there. It's about the only place I know it exists in this state. And when you get groundwater, and that stuff then got laid down, and there might have been more glacial material over it, depending on, it's variable where it's at. But where you get groundwater coming to a lake through a long distance into that stuff, your lakes will have naturally high phosphorus concentration. Potato Lake up in Russ County is a very good example of that same thing. Lake turns greener and green. Another example is Big Chautauqua Lake up on the high end, up on the headwaters of the Red Cedar. Like I said, that lake is about 45 micrograms per liter naturally. Most other lakes with that type of watershed or that type of lake, it'd probably be 15 to 20 micrograms per liter.
Any good solutions?
It's Mother Nature doing what Mother Nature did.
Yeah, you can't control Mother Nature.
If you got lots of deep pockets, you can do some things to strip that phosphorus out, but we haven't done that on any of those lakes. We've just let them be because that's their natural state.
I live on Small Lake Wissota, and I've lived there for 18 years, and every year the bluegreen algae gets worse in my area, and it's kind of like nobody takes it seriously because it's just on the southeast corner of the little lake.
If you live there, you take it seriously.
I take it really seriously.
Yeah.
And, you know, they just keep throwing up these big houses who then clear the land right to the lake and put lawn in.
What's the creek that comes in the little lake?
Paint
Creek, right? Yeah, there's a bit of agriculture in that Paint Creek watershed. And again, you're on another thing I didn't talk about, I didn't have time here so much, but we really saw this on the Little Lake and we see this on the Yellow River Basin also. Another factor that influences algal growth in impounded systems is retention time. How long does that water actually stay in your part of the lake? And what you see as we go low flow with our streams later in the summer, we got less water coming through there, less flushing. And so what we have is then with those, you've got higher nutrient levels in that portion of the lake because of that Paint Creek watershed. Soon as that water stays in that lake over 7 to 10 days, algae get enough generation times off where they can cause those blooms. And when we go low flow late in the summer, that's what we tend to see in the Yellow River portion and in the Little Lake. And it's kind of a natural function of flow, but you still have these elevated nutrient levels there because you're in this impounded system and you got all these wetlands upstream of you and all the farmland and all that stuff delivers phosphorus to the Little Lake.
Any suggestions on?
Well, they're working on it, you know, and this thing on lake time versus people time, we want things fixed in 1 or 2 years. Well, to fix some of these problems like that, get this behavior change out there onto the landscape, it's going to take, I don't know, I've seen some research that shows it takes about a decade for a major behavioral change in a population of us. We don't like to change very much. We get kind of set in our ways, we get real comfortable, you know.
I guess I feel like it's getting worse instead of better. I mean, the problem is getting worse, but I think the behavior is getting worse as well.
Well, I'm not going to argue with that
because
in some situations.
Because it just seems like they just keep putting more and more houses.
Well, you put more and more houses, more and more impervious surface, generates those rates and amounts of runoff, delivers more nutrients, more sediment. You're going the wrong way. You can build with zero impact if you choose to add those expenditures to the cost of development.
Have you talked to zoning? Because
Yeah, I talked to him.
Sorry, I went over.
Thank you always. Thank you very much.
This program was recorded and presented by Chippewa Valley Community Television. Chippewa Valley Community Television is made possible by continuing community support. If you'd like to volunteer or make a donation, you can contact us by calling 715-839-5067 or on the web at www.cvctv.org.